So we'll finish up with concavity today. Concavity and the inflection points. We're going to talk about the second derivative test. All right, so just taking a look backwards, let's look at all these maximums. Can you just pick a color? I'll pick red for mine, and just put a dot on all the maximums. Okay, can you think of something that every maximum has in common?
Concave down.
Okay, so, sorry, Matthew?
Concave down.
Okay, every maximum sits on top of a concave down position. Okay, great. Anything else that's common for every maximum? So like, use a good word that we've talked about using in all of our... Mm-mm. Okay, change. Something's changing. What's changing? It.
The derivative changes from positive to
The derivative changes from positive to negative. There we go. Okay, so there are two things in common for every maximum. You can prove a maximum to me by citing one of two things. Your proof could either be it's sitting on top of a negative concavity section, or it is the first derivative is changing from positive to negative. Either one of those. Okay? All right. So, whoops. So what's a common feature of every max? Sitting on top of negative concavity, or a changing derivative from positive to negative. Those are, as is a summary of the first derivative test and the second derivative test. They're actually backwards. The first one is called the second derivative test. What kind of concavity is it sitting on top of? And then the first derivative test is showing a change of the derivative from positive to negative or on a chart. Okay, those are common features for every max. All right, well, similarly, how would you justify to me something that's common with every min? Okay, Andre?
Oh, I had a question.
Okay.
Would the endpoint be considered a maximum as well, or no?
Yeah. You can't prove an endpoint by its concavity.
That was gonna be fun.
Okay, but yes, we would have this one would be a local minimum. Okay, and the other one would be a local maximum, right? It's not the absolute. All right. Well, let's try again. So, what would be common for every min? Sits at the bottom of a concave up section. Okay, and what else?
You want to answer that one?
Yeah.
You go ahead.
All right, go.
You got that.
Changing derivative from negative to positive.
Very good. All right, sitting on the bottom of positive concavity and changing derivative from negative to positive. That is a summary of what we've learned last week to this week, all kind of in a nutshell. Okay, so that is called the second derivative test. A maximum, the presence of a maximum can be detected at a critical point. Okay, but first, how do you find a critical point? The first derivative does what? Either set equal to 0 or undefined, 1 over 0. So you find the critical points first, and then the presence of a max can be detected if that critical point is sitting in a negative concavity section, then it has to be a max. Or if it's sitting in a negative, positive concavity, it has to be a min. Sometimes on quizzes and tests, I see people like in the air going like this. Okay. Okay, it's concave down, okay, max, got it. Or concave up, oh, okay, min. Like whatever it takes to visualize it, sketch it on your paper, whatever you've got, okay? All right, so you'll take your endpoints and your critical points. Remember, critical points the only way to get critical points is to set f prime equal to 0 over 1 and 1 over 0. That's the only way. But don't forget your endpoints too. That's one of the most common mistakes, is to forget your endpoints. And then once you have that, you can perform the second derivative test. So this is giving you options. You have the option of the first derivative test, in which you would have to use the word change in it to me. Or you have the option now of using the second derivative test, which you can just cite the kind of concavity it has and whether it's sitting perched on top of a certain negative concavity or based out on the bottom of positive concavity. All right, so here's your arguments. If f prime of c is equal to 0, and I'd like you to add or 1 over 0 to both of these, because that is an important part. If you start out with something that's equal to 0 and 1 over 0 in the first derivative, then check the second derivative to find out the concavity. So this part of it right here is where you check concavity. And then you'll be able to prove or to determine, do I have a local max or a local min? You are not going to be able to find an absolute unless you go back and additionally check the y value from the original equation. Okay, you cannot determine an absolute unless you've checked its y value. So let's try these a couple times. Okay, find the local extreme values using this new option of a second derivative test. So first steps, I always would say, ask yourself if there are any endpoints. Just get that out of the way. Well, actually, you know what should the first question be? Is it continuous? That should be the first question. Okay, this is continuous. Therefore, I can move on. Ask yourself if there are any endpoints. This is a cubic. Does a cubic have endpoints? Okay, so there are none. Then move on to the critical points. The critical points will be finding that first derivative, which is 3x squared minus 6, setting that both equal to 0 and equal to 1 over 0, cross multiplying by dropping a 1, and coming up with some solutions. I get no solutions from the 1 over 0 part. That means that there are no corners or cusps or vertical tangents, which is good because a cubic shouldn't have any corners, cusps, or vertical tangents. Okay. And then the other one is going to give me what critical points? Can you do the math in your head? Plus or minus root 2. Add 6, divide by 3, plus or minus root 2. Now you have a choice. Your choice is either to make a first derivative chart, okay, or your choice is to check the concavity and see if these points are sitting on top of perched on top of a negative concavity or sitting at the bottom of positive concavity. This is your option. I'm going to demonstrate the second derivative test now. So now I'm going to check concavity. Didn't spell that right. So find my f double prime. My f double prime is 6x. So I use that concavity to check rad 2 and to check negative rad 2. When I check positive rad 2, I get 6 rad 2, which is positive. So if rad 2 is a critical point that has positive concavity, where's it sitting? It's a critical point that has positive concavity. You can do it with your hands, right? It's a critical point that has positive concavity, like this. So it must be a minimum, and that is enough proof. A local min. Negative rad 2 would give me negative 6 rad 2, which would be negative, which would imply that x equals negative rad 2 is a local max. It can't be absolute. Whoa, how did I change colors there? Because this is a cubic, and a cubic doesn't have endpoints, and it just goes on forever and ever and ever. Okay, so a cubic is going to go up, up, hit its local max, down, hit its local min, and then just go up forever. So it doesn't have any absolutes. Okay, all right. Let's practice reading a graph. That was an algebra one. Let's practice doing it graphically. Do you see what's highlighted in yellow? Okay, what's highlighted in yellow? This is a graph of the derivative. Some of you are still answering these questions as if I was just saying to you, look at this graph and find the min. Okay, that is a low-level question. That is something that I would ask like an Algebra 1 student, and they would say, oh, the minimum is right here. Okay, I'm not going to ask you that. I'm not going to say this is a graph and find the min. Okay, yeah, we wish. We could only wish. Okay, I'm going to say this is a derivative graph. Find the max and mins of the original graph that you cannot see. Okay, so my best recommendation here, trust your definitions. Don't trust your eyes. Trust your definitions. Your definitions are a minimum needs to change from positive to negative slope. Negative to positive slope. A maximum should change from positive to negative slope. Trust your definitions. So my definition is set the derivative, which is this graph, equal to 0 or discontinuous undefined, and I do see 3 of those. Here's where maxes and mins may or may not happen. Maxes and mins are going to happen at those places, not down here. This is not where a max or min is going to happen. That is not the case. If you would like to make a chart as you're reading that, if that helps you, it would be based on how you would shade this in. Okay, you've got things shaded above the x-axis, and then you've got things shaded below the x-axis. So if you were going to make this into a chart, it would be a plus, it would be a plus, I want the right colors here, minus, minus, plus. That would be how you would interpret that. So changing from a plus to a minus, this guy right here is going to be what kind of value? A max, because it's changing from a plus to a minus. What about this guy right here? 0. Is that a max or a min? It's a minus that stays a minus. Neither. And then this last one will be a minus changing to a plus, which would be a min. Those are my maxes and my mins and my neithers. You can also tell me where it's increasing and decreasing. All right, so we've done this a couple days now. Now I'm going to give you the same picture and ask you to find the inflection points. The inflection points are the maxes and the mins of this graph, because the inflection points are going to be where the slope changes. So what you wanted to do before, you get to do now. These are going to be your potential inflection points. And what is connecting those inflection points, those potential inflection points, are slopes. And so as I read this for concavity, I'm going to read this as a minus slope, a plus slope, a minus slope, and a plus slope. Okay, I'm talking about the slope now. I'm talking about this is going down, and then it changes to go up, and then it goes back down, and then it changes to go back up. What you wanted to do the first time is actually what you get to do for concavity when you're reading a derivative graph. And so the minuses and the pluses now mean concave down, changing to concave up, changing back to concave down, changing to concave up. We're talking about now concavity. So all of these are your concavity values. And so each of these 3 are going to be your inflection points. And you can argue your case by saying there is an inflection point because the concavity changed. That's the because. I'm 100% confident there will be an inflection point at those 3 positions because the concavity is changing. Okay, I want to practice that one more time with a new graph. Are there any questions? Yeah.
Yeah, so like with that first point there, would that be concavity down?
The point isn't concave down, but the whole interval is concave down.
Okay, so the interval before that.
Right, so the interval right here, let's see, so let's estimate that is about, it's about root 2 actually. So this would be x less than negative root 2. That whole region, because the derivative graph has negative slope, that would be concave down. Uh-huh. Okay, here's another one. Okay, this is a graph of the derivative. Okay. Nathan Deere, give me a potential critical point. C is a potential critical point, I would agree. Okay, all right, good. Okay, Luke, give me another potential critical point.
A.
Correct. Okay. David, another potential critical point. E. Okay. Nathan, another potential critical point.
G.
Okay. Andre, another potential critical point.
F,
Why?
because it's a discontinuity.
Yes, because it is a discontinuity. All right. There are 5 potential critical points. Now, to decide what kind of critical points they are, you may want to do shading or do whatever, but we're going to have this section up here and this section all up here, and then we've got these sections down here. Okay? Anybody want to make, okay, so Tyler, make a case for one of those critical points.
A, because.
What about A? What kind of critical point will it be? Can you make your case?
Give me 1 second. Yeah. Oh, it's a maximum. It's a maximum because the derivative changes from negative to positive.
The derivative is changing from negative to positive.
Okay, it's a minimum.
Okay.
Yeah,
All right.
Very close.
Yes, so we have
I
a
got that right.
minus plus, which means this one is a minimum. Okay, all right, Sam? C is a max because,
That goes with positive.
all right. It,
The
the derivative goes from positive to negative. All right, Brendan?
E.
Okay, what about E? Why? Okay, that would be true. All right, Isaac? F?
F. No,
Why?
because it's a discontinuity.
That's not the reason. You're right about it being neither, but it's not the reason why it's neither.
Because it's like both positive and negative.
It's not positive and negative. Okay, look at where F is. Okay.
There's no point
It doesn't matter if there's a point there or not. The original graph could have a point. It could be a corner. It could be a cusp. It could be a vertical tangent. Okay?
It's because the derivative doesn't change.
Okay.
It stays positive.
Okay. What kind of derivative do we have on the left of F? Positive. It's in the green section. What kind of derivative do we have on the right of f? Positive. It's still in the green section. And because there is no change from positive to positive between those two, then it is neither a max nor a min. Okay? All right. Then what about the last one? Okay, Noah, G? A max, why? Derivative changes from positive to negative. Good. Okay, we're getting the hang of this, reading the derivative thing. All right, last one. Now we're going to try for inflection points. Same graph for inflection points. And when you're looking for inflection points, you get to look for the maxes and the mins and any points of discontinuity again. So my candidate, all right, Carla, can you go through what are the candidates for inflection points here?
B.
B is a candidate.
Can I keep going?
Sure, give me all the candidates.
D.
D is a candidate.
F.
F is a candidate. Okay, it's still a candidate because it is a point of discontinuity. So only between these points, so I'll just do some hypothetical separation lines here. If those are the only candidates, then you look at what's going on between those candidate points. And so what's going on here, because it would be considered a plus. And so this is what's telling us about concavity. So what does that plus tell us? If it's telling us about concavity. That's concave up, has positive concavity. And then the next section, its slope is minus, which means it is concave now down. And so what would be happening at B? It is an inflection point because there was a change in the concavity from positive to negative. And then that next section has an entirely increasing, which would change back to a plus, another concave up section, which means another inflection point, and then finally decreasing, so concave down. So every candidate in this situation is an inflection point, because every candidate separates a section from increasing to decreasing. And that's how you're going to read concavity from reading a first derivative graph. Oh, perfect.